Today we begin chapter 2. In chapter 2, we're going to be looking at using what is called deductive reasoning, which is kind of a way of saying logical reasoning built from facts, not from assumptions or observations, but from facts. Today we're going to talk about something called if-then statements. An if-then statement, the third one down, also says that it's called a conditional statement. It has a condition to it. So they usually come in the form of if-then. We call the if part the hypothesis. This is different than hypothesis in science class. So in science, when we say hypothesis, we mean like a guess or a prediction. That's not the case in geometry. When we say hypothesis in geometry, what we mean by that is a condition that has to be met. So given that something occurs, what's going to follow after that? Okay, so be careful about that definition when we roll around to the quiz on Friday. If I ask you to define hypothesis and you say something about an educated guess, that's the science word. Okay, so here we're not talking about that. A hypothesis is a condition that has to be met, is the if part of the statement. After that, we have the then, or the conclusion. So if this hypothesis occurs, what naturally is going to follow from that? If-then statements are really, really common in the way that we speak naturally. If you start listening for them, then you'll hear them all the time. Did you notice that? If you start listening for them, then you'll hear them all the time. That's just the way we talk. If it's sunny, I'm going to go to the beach. If it rains, I don't think I'll go to the football game. We put these conditions on things all the time, and that's an if-then statement. A converse takes the if and the then and interchanges them. The words if and then actually stay where they are, but the body of that switches around backwards. Okay. A counterexample is something that we disprove a conditional statement with, and it only takes one. We just need to find one way to show that this won't work, and that completely disproves it. Even if it works hundreds of other ways, if we can find one way that it doesn't work, that makes it a false statement. So these are some examples of statements and their converses. A statement could be, if Ed lives in Texas, then he lives south of Canada. Yeah, okay, that makes sense. If he's in Texas, he's south of Canada. The converse takes the bodies of those and switches them. So if Ed lives south of Canada, then he lives in Texas. Not necessarily, right? We're south of Canada, but we're not in Texas. So sometimes a statement can be true and the converse can be false. Just because a statement is true doesn't mean we can start messing with it and have it stay true. Another example, a more algebraic statement, if 4x equals 20, then x is 5. Okay, that works. If x is 5, then 4x is 20. Yep, that's still true. So in this case, both of them are true. Just because a statement is true does not mean its converse will be true, but it can be, so we always have to test it. We have to look for that counterexample. So for the first one, our counterexample would be us. We're south of Canada, but we don't live in Texas. Okay? When you come up with a counterexample, the if part still needs to be met. Okay? So we still need to find something that's satisfying the condition. So we still need to find something south of Canada, but we want to try to find something that's not Texas. Okay? Questions? Conditional statements do not always come in if-then form. It's the most common form, but there are some other forms here. So beware of these. Our general is the if P then Q. Hypothesis then conclusion. We can also say that P implies Q. Our hypothesis implies that our conclusion has to happen. We can say P will happen only if Q. The one you really need to watch out for is this last one that says Q if P. Because that guy's backwards. So we get in the habit of always thinking hypothesis, conclusion, hypothesis, conclusion, hypothesis, conclusion. But in this last one, Q if P, they're backwards actually. This one says conclusion if hypothesis. So you got to be careful of that one. Keep an eye out for in the middle of a statement that has just the word if. The one before says only if, and that still came in the normal order. But we got to keep our eyes out for the one that says just a plain if in the middle of it. Then they're actually coming backwards. A biconditional statement can be written if both the statement and its converse are true. Okay, so it doesn't always happen. But if both the statement and its converse are true, we can write it as a biconditional statement. We write one of the pieces, and then we use the words if and only if, and then we write the other piece. If and only if, we write a lot in math, and so we get sick of writing the same thing over and over, and so we come up with all these symbols or abbreviations, and IFF is the abbreviation for that. So if you see IFF, it's not a typo, it's not like I just got carried away while typing the word if. It actually means something different. It means if and only if. It means it's a biconditional statement that it is true whether you read it forwards or whether you read it backwards. Every definition can be written as a biconditional statement, because definitions are true no matter what. So we could say congruent segments are segments that have equal length. That's our definition of congruent that we learned in our last chapter. Congruent segments are segments that have equal length. We can write that as a biconditional by putting the words if and only if into it, by saying segments are congruent if and only if their lengths are equal. And this is true either way we read it. We can say segments are congruent if their lengths are equal, or if their lengths are equal, we can call them congruent. Okay, so it works both ways. That's biconditional. In this first type of example here, on your homework, this will be the first type of question as well. You need to state your hypothesis and conclusion. On your notes, you can just like underline and circle, which is what I'm going to do. I'm going to underline the hypothesis and circle the conclusion. However, when you're in your textbook, you can't really do that, right? You'll actually need to write them out on your assignment. So remember that in general, they come in the order of hypothesis conclusion, but there's the one special case that we have to watch out for. And what is that?
Q if P.
Q if P. If it's just the word if in the middle of the statement, they're coming backwards. So the first one, if then. That's coming in the normal order. The second one, if she's smart, then I'm a genius, comes in the normal order. Okay? If then. Notice that the hypothesis and the conclusion don't actually contain the words if and then. So when I'm underlining or circling or on your homework when you write, don't include the words if and then. The hypothesis and the conclusion are just kind of the bodies of those phrases. Okay. Implies, that one comes in the normal order. So our hypothesis comes first and then our conclusion. Next one, RS is 1/2 RT if S is the midpoint of RT. That's got that danger in it where it's just the word if in the middle there. So this is the one that comes backwards. S is the midpoint of RT is the hypothesis. RS is 1/2 RT is the conclusion. Okay? When it's just the word if in the middle of the sentence, they're going to come backwards. That happens again in the next one. The final one says only if, so then they come in the normal order. What do you notice about these last two statements here? Focus on these two statements. What do you notice about them? They're the same except they kind of switch jobs, right? So if we put the two statements together, the congruent got to turn to be hypothesis and conclusion. And the measures being equal got to turn to be hypothesis and conclusion. And those are both true statements because congruent means equal size and equal size means congruent. So what we can do is combine those into a single statement that we call a biconditional. When you combine into a biconditional, you pick one of the two phrases. It doesn't matter which one. So I'll start with the congruent piece. But you could start with the measure piece. It doesn't matter. And then we say if and only if, or IFF if you want to abbreviate it. But it's if and only if. And then the other piece. And this means that this statement is true no matter which part is the hypothesis and which part is the conclusion.
So what's the difference between if and only if and only if?
Only if still has one hypothesis and one conclusion. If and only if means either one can be the hypothesis or the conclusion. So it's just that one little extra word we got to watch out for that makes a difference. All right, these questions ask us to provide a counter example to show that each statement is false. You can use words or a diagram. I'm going to tell you some of these are going to feel very true to you, but they are all false. Okay? Each and every one of these statements is a false statement, so there is some way to disprove it. The way we disprove a problem is with a counterexample. It doesn't matter how many drawings you can make that it actually works for. If you can make one drawing that it doesn't work for, the statement is not totally true then. So that's our goal on these 4 problems, is to find something that doesn't work. When you're doing that, the if still has to work. So in the first one, you have to draw a picture that has AB and BC being the same size. That's our given. That's our starting place. That has to be true. But we want to draw the picture in such a way that the then doesn't work. Okay? So the if has to work. We want to show that that doesn't mean that the then is going to work as well. Okay? So take a few minutes. Go ahead and try to think about these. You can talk to a couple people around you and see if you can come up with some counterexamples here.
Are we going to go over that?
Yeah. Did anybody come up with a drawing or an example for the first one that shows that it doesn't have to work? What did it look like?
Kind of like an angle shape.
Got it. So what we can do is have AB and BC be the same size, but not in a line. If they're all in one line, this is a true statement because that's what midpoint means. But we weren't told that they're all collinear. So if it turns a corner, we can have 2 congruent segments, but without a midpoint. Okay? So that would be our counterexample for the first one. We can't have 2 separate pieces, though. That's something students will often want to do, is make like an AB and then a completely separate BC. But B is just 1 point. So they do have to come together. We just don't want them to come together in a straight line. So that first one, we can have A, B, and C. B has to just be 1 point, not 2 different points, but we don't want them to all be in one line. All right, the next one. If a line lies in a vertical plane, then the line is vertical. Okay, so remember we thought about like a plane could be like a sheet of paper. So if I hold a sheet of paper straight up and down, that'd be like a vertical plane. If I draw a line on that paper, does it have to be vertical? No, right? So I can have my plane be vertical, but my line could be at any angle. I don't have to draw the line straight up and down just because the paper's straight up and down. So that'd be for the second one. The third one, if a number is divisible by 4, then it's divisible by 6. So what's a counterexample there?
16 isn't divisible by 6.
16. 16 is not divisible by 6, but it is divisible by 4. Anybody have a different one? 32. Divisible by 4, but not by 6. 4 itself is, right? It's divisible by 4, but it's not by 6. 8, right? So there's a lot of counterexamples we could come up with for this one. We just need to find a number that divides by 4, but that doesn't divide by 6, and there's a lot of those. Okay? 24, okay, so that's not a counterexample. That's a place that actually works. 48, that one actually works, but there's a lot of numbers that don't work. 12 actually works. There's a lot of numbers that don't work. The last one, this one is pretty tricky for a lot of students. If x squared equals 49, then x equals 7. X could be 7, but there is something else it could be.
-7?
-7. Because if you square a negative number, a negative times a negative is a positive. So a lot of students struggle with that one, but now that we've done this, be prepared to see it again, okay? Remembering that when we square a negative number, it becomes positive. So anytime we see this squared situation, we should also think about the negative possibilities there, okay? Questions? Okay, for these, we're asked to do several things. Tell whether the statement is actually true or false. State the converse, and then decide if the converse is true or false. Okay, so several things to do here for these. So the first one, if today is Friday, tomorrow is Saturday. Is that a true statement?
Yes.
If it's Friday, could tomorrow be anything other than Saturday? It's got to be Saturday. So that's a true statement. To write a converse, we leave the if where it is, we leave the then where it is, but we move the bodies of those phrases. So our converse is going to be if tomorrow is Saturday, then today is Friday. The if and the then actually stay where they are. That's a big mistake for students. They'll take the whole thing and switch the orders. Make sure the words if and then stay where they are, but that the bodies of the phrases switch positions. Now, is that a true or false statement?
True.
That's true. If tomorrow is Saturday, it must be Friday today. There's nothing else that can come before Saturday. So that statement is still true. For the next one, if x is greater than 0, then x squared is greater than 0. So if x is greater than 0, that means it's a positive number. If I take a positive number and multiply it by itself, is it still going to be positive? Yes. Okay, so that's true. Our converse leaves the if where it is, but then switches the insides. So if x squared is greater than 0, then x is greater than 0. True or false? False. We just had an example of this where we said x squared was 49, right? 49 is a positive number, but we said one possibility for x is negative 7. So just because a square is positive doesn't mean our starting number was positive. So that statement is false. The third one, if a number is divisible by 6, then it's divisible by 3. True or false?
True.
True. I was trying to say true, so then I said tree. So that is true. If it divides by 6, it has to divide by 3 because 3 goes into 6. So that's a true statement. When we flip that around, we leave if in its place and then in its place and switch them. Now here's kind of a grammatical thing. I'm not going to mark you off for this. But if all I do is just switch the bodies, I would say if it is divisible by 3, then a number is divisible by 6. Now technically, grammatically, we should probably have a noun before a pronoun, right? Right? We all learned that. So I'm not going to mark you off for it though, okay? If you just switch the parts, that's fine. But grammatically, it'd probably be best to say if a number is divisible by 3, then it is divisible by 6. Kind of leave the noun and the pronoun where they belong. But if you switched it, that's fine. So if you just said if it is divisible by 3, then a number is divisible by 6. I would not mark you off for that. Is that a true or false statement?
False.
False. What would a counterexample be?
3.
3 itself would be a counterexample. 9 would be a counterexample. Lots of counterexamples. There's lots of numbers that divide by 3 but don't divide by 6. Last one. If 6x equals 18, then x equals 3. Is there anything else x could be? Or would it have to be 3? It'd have to be 3. That's the only thing I can multiply by 6 and get 18. So that's a true statement. I turn it around, I get if x equals 3, then 6x equals 18. That's a true statement as well, because 6 times 3 has to be 18. It can't be anything else. That's the only thing it can be. So that is also a true statement. Questions on that? How to decide if it's true or false, or how to write a converse? Okay, your homework is printed here, but I have one extra assignment that I'm going to pass out for you. And by the way, in this packet, some of the spacing got off. So if at the bottom of a homework assignment you don't see the homework printed, look at the top of the next page. You do have homework every night. So it just, some of them, the spacing got a little off. So if it's not the bottom of the page, look at the top of the next page. So this homework is due tomorrow. But I have another assignment for you that's going to be due on Friday. For this assignment, and I will pass this out to you, so you'll have all these directions, but it says find 5 Bible verses that are in conditional format or could be written in conditional format without changing the meaning of the verse. The Bible is full of conditional phrases. Okay? There's actually one book of the Bible that like almost every verse is actually a conditional statement. But Jesus used a lot of conditional statements as well. There's a lot in the Torah where God promises that if his people are faithful, then he will bless them. Okay? So there's a lot of conditional verses in the Bible. Your job is to find 5 of them. And then for each of those verses, give the reference. Tell me where is that verse. Okay? Write out the verse as it is. Write out the converse of the verse. And then decide if the converse is true or false. And it's okay for the converse to be false. A lot of students really struggle with writing that because you feel like you're saying that the Bible is wrong. We're not saying the Bible is wrong. We're saying order matters. That sometimes promises are given on a condition. So like when God says, if you're faithful, then I will bless you, he's not necessarily saying he's going to bless you no matter what. We got to hold up our end of the bargain too and be faithful. So it's okay to say that a converse is false. So you're going to find 5 of them and do that. So here's an example. You can't use this one. Matthew 7:7. I reworded it slightly just to make it into the if-then, but the meaning is still here. If you ask, it shall be given. If you seek, you shall find. If you knock, the door shall be opened. Okay, there's actually 3 of them in there. The converse would be, if you are given, then you will ask. If you find, then you will seek. If the door is open, then you will knock. Yeah, probably not. If I already found it, why am I still looking? If the door is open, why am I knocking? Right? If I already got it, why am I asking for it? So that doesn't really make so much sense when we turn it around. Okay? So your job by Friday is to find 5 of these. I don't care if you write them or type them, as long as if you write them, your handwriting is legible. Okay? Questions?
Do we get our card?